So a phase line with one equilibrium point, that's a sink. Both arrows point towards the equilibrium point. So you've got your phase line, an equilibrium point, and the arrows point towards it. It's a sink. Is dy dt equals y squared autonomous? Yes. How about dy dt equals t squared? No, correct. Depends only on y is autonomous. Yeah. Okay, so a phase line is another qualitative tool we can use to study solutions of autonomous differential equations. So it only works for autonomous differential equations, which is when the right-hand side of your differential equation has only y's. All right, so the first qualitative tool we looked at was slope fields. But here's a slope field of an autonomous differential equation. So you might notice that there's a lot of redundant information in this picture. Because the slopes of the tangent lines don't depend at all on t, horizontal lines all have the exact same slope, right? Yes, yes, you definitely did. So there's a lot of redundant information in this picture because for all t's you have the same slope, right? It only y changes the slopes. Okay, so there's so much redundant information here. We're going to try to compress it into a single vertical slice of the slope field. I don't need to look at that whole line. I just need to know one spot, what it does at one t value. Okay, so we compress it into a single vertical line that we call a phase line. We mark where dy dt is 0, and then we also indicate the sign of dy dt at the intervals in between the equilibrium points. So we do lose some information because you don't get the exact slope, but we just know whether it's positive or negative. So we lose some information, but we also compress it into a much cleaner picture. All right, so let's see, dy dt is y minus 2 times y plus 1. So I want to find equilibrium solutions. When you put them on a phase portrait, we often call them equilibrium points. But equilibrium solutions, how do you find them? Set the derivative equal to 0, because equilibrium solutions means functions that don't change, constant functions. Constant functions have a derivative of 0. So we take the derivative, set it equal to 0, and we get y equals 2 and negative 1 as my equilibrium solutions. We put them on a phase line as points. So we've got a vertical line, we put on negative 1, and we put on 2. Those are our equilibrium solutions. Okay, now we have to look at the sign of the derivative, the sign of the dy dt, in between each of your equilibrium points. So if y is bigger than 2, look at your dy dt. If I plug in a y that's larger than 2, like say 5, right, do I get a positive value or a negative value? Positive. So yeah, so 5 minus 2 is 3, 5 plus 1 is 4, 3 times 4 is positive 12. So the fact that I could actually calculate values, I would use that if I was making a slope field, but in a phase line, I only need to know that it's positive. So it's positive, we put an up-facing arrow. All right, pick a value between negative 1 and 2. 0. Okay. If you put 0 in for y into the differential equation, do you get a positive or a negative value? Negative. So we put a down-facing arrow, because dy dt is negative there. All right, and then put in a value smaller than negative 1. Negative 100. That's going to be a negative times a negative, which will give you positive. Positive. So we put an up-facing arrow. 2 is not a node. What is 2? 2 is a source because everything goes away from it. So yeah, 2 we label a source because everything is going away. Both arrows point away, so it's a source. And then negative 1, everything is going towards it. So that's a sink.
So the difference between a source and a node.
In a node, one side goes away and one side goes towards. Yep. We'll draw a picture of it in a minute. I got a spot in the notes for it. So this is a phase line. This is a phase line for that autonomous differential equation. We can use the phase line to sketch solutions, y of t solutions. They aren't as accurate as ones we would get if we used a slope field, a whole slope field, or Euler's method, but they can give us really good information about the long run behavior of a function, okay, of the solution. So I'm going to re-sketch my phase line over here. 2, -1, up, down, up. Okay. And then I'm going to use all that information to draw a solution y of t. Okay. So my solutions are in the ty plane, right? Solution to a differential equation is a function y. And I can use this information to sketch it. So I know I have equilibrium solutions at -1 and 2. So I put -1 in. That's an equilibrium solution, a constant solution. So the function y does not change in time. And then I have another one at 2. Constant. And then I can pick any initial values in between there and use the phase line to know what's going to happen. Because if I know the sign of the derivative, I know what the function itself is doing. So let me pick that random initial value of 0. Y of 0 is 0. So I'm between -1 and 2. So my derivative is negative, right? All right, so when a function's derivative is negative, what does that tell you about the function itself? It's decreasing from Calc 1, right? So as I move from left to right, my function has to be decreasing and go through that point. So it's going to go down towards my equilibrium solution over here, and it's going to go up like that over here. And again, this is really a rough sketch. I don't know exactly what it does, except that it's decreasing. So it's hard to know exactly how fast it's decreasing, but it gives me information about the long run behavior. How do I know that it doesn't cross that equilibrium solution? Because of the uniqueness theorem. Yeah. The uniqueness theorem is what tells us that solutions can't cross, right? Solutions can't cross. Right, because my initial, my function on the right-hand side of the differential equation, this guy, that's a polynomial. It's always continuous. Its derivative with respect to y is always continuous. So we have satisfied existence and uniqueness. So we know that solutions can never cross. Let me pick another random initial condition. What if I put one right here? Less than -1. This arrow says that I'm going to go up towards -1. Right? So it's going to be increasing. Yeah, the derivative is positive. This is an increasing function. So something like that. And this must have to go down like that. You know it doesn't flatten out again asymptotically, or there'd be another equilibrium solution. And then I could put another initial value up here. And what does this say happens? It's increasing. So that goes up like that. And it must come up from the equilibrium solution. Yep, and you can see all of this information from the slope field also. Yeah, in a much more accurate way. The slope field is much more accurate. The phase line gives you really compact information about the end behavior. Yeah. Yeah. Right. This is just qualitative. Yeah. Yeah. Okay, so equilibrium points can be classified as a sink, a source, or a node. We already talked about sink and source, right? So a sink is when the arrows both point at the equilibrium point. A source is when the arrows both point away from the equilibrium point. And a node is when you have one of each. I don't know. So either they both point up or they both point down. One points towards and one points away from the equilibrium point. So if you look at our original graphs up here for a sink, -1 was a sink, and you can see that the solutions approach that equilibrium point from above and below, right? So it's a sink. So as time marches forward, everything just gets drawn to that equilibrium point, or that equilibrium solution. Whereas 2 is a source, so as time moves forward, everything just goes away from that equilibrium solution. Solutions, shorthand for solutions. All right, and then a node, if you were going to sketch the solutions when you had a node, right, here's your equilibrium solution. We would come down towards it from one side and go away from it from the other, like that. Something like that. Okay, I'm going to have you work on your activities, but we're going to save the last 10-15 minutes of class to do the very beginning of 1.7, because there's a lot to 1.7, and it uses a lot of this phase line stuff. So I think it'll be good to do some of it today.